Welcome to the Neural Implant Podcast, where we talk with the people behind the current events and breakthroughs in brain implants in an understandable way, helping bring together various fields involved in neuroprosthetics. Here is your host, Laden Yurachek.
Hello, everyone, and welcome to the Neural Implant Podcast. Today's guest is somebody who is very famous in the brain-computer interface space. It's Dr. Miguel Nicolelis, but he's actually more famous because he is a famous footballer, and he played in 2014 World Cup for FIFA. Do you want to talk about this a little bit?
I didn't quite play, but it was very amazing to be on a soccer field in the opening day of the World Cup here in Brazil to do a scientific demonstration. And we worked for 18 months to get to that day, and more than 150 people around the world from 25 countries contributed to the research. And when Juliano Pinto delivered the opening kickoff of the World Cup using the first brain control lower limb exoskeleton, it was quite a moment. So every Brazilian kid dreams to play for the Brazilian national team on the World Cup game. I didn't quite fulfilled that dream, but I got as close as a scientist can get. And we had about 65,000 people in the stadium that day and about 1.2 billion people watching the kickoff. And it was quite a moment to see. And for Juliano, of course, who before the accident a decade ago, he was an athlete, a track and field Olympian. And of course, he had a very serious spinal cord injury, a very high level, thoracic 4 level. He had to recalibrate his entire life and become a Paralympic athlete. And he was actually training for the trials of the 2016 Olympics here in Brazil, Paralympics in Rio. But he devoted about 6 months of his life to train very intensively for that kickoff. So it was and if you think that, they materialized after 30 years of research, so it was very, very nice.
Yeah, no, that's really fascinating. And I had heard about it like on the news everywhere. Everybody was really excited about it back then too. So definitely very popular to very famous. So that was quite an achievement. So yeah, pleasure to have you on the show. Do you want to introduce yourself a little bit beyond this maybe this famous part and talk about yourself, what you've done?
Yes, as you said, I went to medical school and got my PhD here at University of São Paulo in Brazil. In 84, I got my medical degree. 88, I got my PhD. And then I decided to do a postdoc in the US. And I was, of course, looking for someone who would be interested in the same idea I had at that point, which in the late 80s was almost crazy. Every neuroscientist that I talked to in Brazil, or the people I wrote letters because we didn't have email at that time, you had to wait months to get a reply from a famous neuroscientist in the US or Europe. I wanted to record the electrical signals from large numbers of neurons at the same time, not one neuron at the time, as everyone was doing at that time. And everybody wrote back to me and said, oh, no, that's pretty crazy. It's not going to happen. It will take a lot of investment. This is like a Manhattan project for neuroscience. But one guy replied to me, John Chapin. And he had the same idea that we could not move forward without doing that. And long and behold, he invited me to visit him in Philadelphia. And I went there and we spent 3 days together, and it was clear that independently we had come up with the same kind of research program idea. And he was, of course, 10 years senior than I was, but a very open-minded guy and a very friendly, wonderful intellect, and a typical guy from Colorado, where he was born. Very adventurous, was a huge skier, almost killed me twice trying to teach me how to ski in Colorado. And it was almost the end of my career. But no, I moved to the US in 89 just to develop the technology and the approach to record from large numbers of neurons. And it was basically occupied me for my entire postdoc of 4 years there in Philadelphia with John. And when I moved to Duke and I created a lab divided both into basic science into rodents, like what I did with John, but also create a spin-off to do research on monkeys, which I thought was fundamental to prove that what we have developed would work. Juncture, John and I realized that we had to have something to demonstrate to the neuroscience community that the ability to record from 100, 200 neurons simultaneously could have a very big impact, not only on basic science, but on applications of this technology. And that's when we coined the term brain-machine interface. And when we decided to link a rat to a tiny 1 degree of freedom robot to see if the rat could learn to control their lever back and forth and get water transported by this robot arm. And when we did that, I remember 1999, and we soon realized that neuroscience would not be the same, or systems neuroscience would not be the same. And that was actually, we celebrated just 22 years of that paper. And that paper opened up the whole thing because it was the first experimental demonstration that with this technique of recording from large numbers of neurons. People don't realize, but the first BMI that worked experimentally was in a little rat with 48 neurons, but it worked. And a year later, we had 100 neurons in monkeys. So it paid off to have divided the lab at Duke since the beginning into a rat lab and a monkey lab.
And then you took over the monkey lab, right? Or the rat lab. And then
I created it. There was no monkey lab when I got to Duke. So
and then what's the advantage of monkey versus rat versus pig, all these different animal models versus human?
Yeah, but pig, I don't see any advantage. Pig, I see it for a good Brazilian barbecue. But only Neuralink thought that they could get anything done with a pig. I never understood that. But the monkeys, of course, you can train the monkeys to do much more sophisticated tasks. And they are closer as experimental models to the cortex that we humans have. And they're more accepted by the neuroscience community as models of human behavior. And so we wanted to do more sophisticated stuff as we actually end up doing in 22 years of work. You could get social interaction tasks using BMI. You could have bimanual BMIs, which is proved to be a very important development because you cannot get rats to play with both paws in a very sophisticated way, but you really can get monkeys to do very sophisticated bimanual tasks. And also, when we came up to the conclusion that we had to abandon anesthetize and immobilize preparations, we had to use freely behaving animals. It was obvious that monkeys would give us a much closer model to human behavior than rodents. And it turned out that we made discoveries that we never expected, like finding coding of space, what people call place cells, in the primary motor and somasensory cortex, not in the hippocampus, which to this day, 4 years after the paper has been published, has been causing a lot of commotion. Because first, it's always like that, but people didn't believe. It's impossible. No, you cannot have found place cells in the primary motor cortex. It has been reproduced now by independent groups. And now you need to explain it. After all, people thought, you only see that in hippocampus because hippocampus is the top of the hierarchy, the cortical hierarchy. I never believed in a hierarchy, neither did John. And we are proving this point 20 years later, you can find very complex cell behavior, even in what people consider lower level cortical fields, like the motor cortex. So it was very important to add monkeys to this. And because of the technique allowed you to record for years, once an animal is implanted, to give an idea, in 1 decade of work, from 2006 to 2018, we use only 8 animals. So you could reduce dramatically on the number of animals that you needed for research. So that was also very important.
And is that just because the monkeys were more gentle on it, or why? Or maybe they're longer lived, or why?
No, because the microwires, the flexible microwires that we used basically got encapsulated by the inflammatory reaction around them, and they move with the brain. They didn't destroy the brain like the rigid daggers of the Utah probe, for instance, that cut through the tissue, and that's the reason they only last a few weeks maximum. No, that's the reason John and I, way back in the 90s, opted for these flexible filaments, metal filaments, because we realized that if the electrodes would move with the brain, they wouldn't cut through the tissue. They wouldn't damage the tissue. And since the tips are relatively large, the inflammatory reaction doesn't clog the tip. And it works on your benefit. It creates a high impedance electrode. And that allowed us to have very beautiful signal to noise ratios and longevity, recordings that could last for years. In fact, we documented in one monkey from 2009 to 2017, We recorded the same animal continuously in different studies, of course, but not necessarily the same cells, but for all this time. But you could keep cells for months, the same neurons. And that proved to be a proof of concept that if that needs to be done in humans, in some circumstances, that these microwires probably are the best candidates for long-term human implants.
Yeah, definitely. I think that does make much more sense. And then I guess there's less retraining if it is the same neurons. But I'm curious. I want to go into this hardware that you've used. You made your own. It sounds like you made your own probes, and then I'm imagining computers from the late '90s too. So were you limited by that?
There are very great stories about programming computers in the late '80s, early '90s to do all these experiments. And John was a phenomenal programmer. And I have to learn to use all crazy machines that he had in his lab because he was a computer connoisseur. And he was always seeking for machines that you never heard about, Eclipse. I grew up working with PDP-12, and I thought I was a saint for having survived a PhD with that machine. But the machines I found in John's labs were completely insane. That's what you had. And think about it, having 64 kilobytes to program. The RAM was 64K, and you're trying to record 48 neurons simultaneously. It was like when I watched, many years later, when I watched this show or this movie about the computers that they used during the Apollo program, I felt very sympathetic for those guys because John and I were doing the same kind of nutty programming job to survive. And then when I moved to Duke, when we started doing monkeys and suddenly we're recording 100, 200 neurons, we had a wall of PC boxes that we hook up together. And every time one of my students complained about the programming job, I said, "Are you kidding me? You have 1 megabyte of RAM. We had 64K. No complaining anymore. That was plenty." But it was there are many funny stories on, like when working with my good friend, Gordon Sheng at the Technical University of Munich, we wanted to do this. He was in Japan at that time, ATR in Kyoto. And we wanted to have our monkeys controlling his humanoid robot in Kyoto. But we have all these firewalls. This was 2005, 2006. We have all these firewalls in the universities and ATR. And Gordon basically became a hacker for a weekend. And he went around all the firewalls between the US and Japan in a weekend, allowing us to send the signals from the Idoia, our monkey, brain signals to Japan, allowing the robot to walk, and video feed coming back to Idoia so she could see the robot. And months later, the Japanese Internet Authority or something like that was warning ATR that someone inside the building was hacking firewalls all across the Pacific. And that was Gordon, and nobody found him out. It was very funny. We had to do all sorts of things to because, of course, internet was slow. Even our first paper on monkeys in 2000, we had a robotic arm at MIT in Boston and one at Duke. And our good friend there, his students had to work out a protocol to get the same monkey to control both robots at the same time. But you had this delay from transmitting the signals from Durham to Boston that had to work out because we wanted to inform the monkey that he was doing okay. So we could write a book just on the history of brain-machine interfaces and the computing that went through, that was necessary to through. The efforts were pretty crazy.
That sounds crazy. How do you even do that? That's like, 64 kilobytes for 48 probes. That's like one kilobyte per probe. And are you writing it to memory right away, or is it just?
No. We are dumping this thing down directly to this huge. You had to mount to the hard disk. You had to, and John was programming, and not me. I never did that, but he was doing in hexadecimal programming, and he was a genius in doing this kind of thing. And I learned to operate the Eclipse machine on a high-level language. And even that was a pain, very painful. But you enjoyed that. We had many good stories because think about it. The first day that we recorded 48 neurons, and it was not on one single location in the brain, it was distributed across multiple structures. Nobody had ever seen a sensory pathway in real time. What is going on? A rat is walking around and you're recording through the entire somatosensory pathway. And to both of us, 3 a.m, watching this on the computer screen, monochrome, just to make sure. And John looked at me one moment and said, at least we have something that we can tell people. I said, what? I'm thinking he's going to say something profound about the dynamics of the somatosensory system. He says, no, we can tell our grandchildren that we share the same lawyer for our divorces, but who is going to believe that at 3:30 in the morning we are looking at 48 neurons? And that's what we're doing. And it was fantastic. It was a feeling of watching something that nobody has ever seen before. It's like discovering a new galaxy or something like that, because it was counterintuitive. It was not what people thought. It was the dynamics was much richer than people thought, because people had only watched individual neurons in anesthetized animals, and that was completely different from a fully behaving beast.
Wow. Yeah, no, that makes sense. And that must have been huge. And it sparked so many more studies too. And okay, so this is a silly, stupid question, but is it easier now with more RAM, better computation? Is it like we have a million times more, but is it a million times easier, or how does that translate, I guess?
Well, it's easier from the computational aspect, sure. But since the questions and the experiments became more sophisticated, once we decided a few years ago in 2017 to do experiments with 2 monkeys or 3 monkeys simultaneously, and in fact putting 2 monkeys side by side in a lab room, and to watch a social interaction for the first time, recording from both brains and seeing something that I didn't expect, that this interbrain synchronization, highly synchronized activity coming from both motor cortex as a monkey observes the other. And as one monkey is a higher ranking order than the other, so one is the alpha monkey, let's say, the colony, the other is the lower ranking delta monkey. And you realize that the motor cortex is coding social parameters. It's coding the distance between the animals, but is only relevant if you are, for instance, the synchronization is maximal when you are basically looking from the perspective of the delta observing the alpha monkey. So you realize that the motor cortex is coding for reward, is coding for social ranking, is coding for place cells, or for space. It's coding for all sorts of things, visual inflow, it's coding for action at a distance, much more than just the motor parameters that we thought when we began this thing. So brain-machine interface, to some degree, open up a huge venue for basic science. And it allowed us to make discoveries that we never expected to make. Like, for instance, Juliano and the other patients that participated in the World Cup, we never expected to see them partial recovery in terms of neurological functions, recovering sensations of visceral functions. We never expected that. And suddenly, a month after the World Cup, we discovered that they were basically undergoing this huge, immense clinical recovery process, thanks to brain plasticity, of course. But that was not expected when we first proposed to use BMI on clinical settings. And now people doing stroke research and other areas, they are showing the same thing. So it got easier from a technical point of view, but the moment you enlarge the questions you can ask, of course, the experiments got much more challenging.
Yeah, definitely. It definitely seems like it opened the floodgates, and many more things were possible since then. And I guess we can move to the future a little bit. Neuralink had this really interesting presentation with the monkey playing pong, but probably for you, that wasn't nearly as innovative. Do you want to talk about this a little bit?
Well, there's several magazines that call me to ask my impression. So, well, that's very nice to see that they're reproducing something that we did 20 years ago. But funny enough, they're doing only in one dimension. We did in 3 in 2002. I don't know what 2003. I don't know what is going on. Well, my students went to work for Neuralink, and one was until recently the CEO, Max. And I'm still not convinced that Neuralink is for real. I don't see much besides a techie gizmo development kind of idea and a lot of fanfare and sci-fi. Bad sci-fi by Elon Musk. I'm not very fond of the projections he makes because 90% of them will never happen. They simply cannot happen. It's not just that it's difficult or it will take time. It's basically against the laws of physics. And that's a little difficult to overcome, even with a lot of money. I have seen better effort in terms of more serious efforts. And the The pong thing convinced me. If the pig had not convinced me, the pong convinced me that, hey, sure. Because first was, we did the first wireless. It was not. First wireless was done in our lab and published in Nature Methods on the cover of the magazine. And the guys who were in the lab at that time, they knew about it. So that was not the first. Then the second was, is large scale thing that allowed to do, and I see a pong game. And I am not the only one. Most of the people in the community, researchers, were not that convinced that anything new had showed up over there. So that's the problem. You have a lot of companies in the space, and not everyone has a clear vision of what is going to do. And of course, these companies need to make money, and none of what Neuralink has shown will make. That I can tell you. And because I have talked to very serious people that did very serious business analysis of this space, and is almost unanimous that is not going to work. Because the number of potential patients that may need to be implanted is tiny, is very tiny. And in fact, the fact that you can do so much with non-invasive technology shows that if you are looking for a profit, it's not what you're going to find in that kind of approach. Of course, for some patients that have certain conditions, you may need to do implants, and for things that we don't even know. For instance, we have discovered that if you stimulate the spinal cord electrically, you can treat Parkinsonian patients, and you can treat chronic epileptic patients in which drugs don't work anymore. And this requires a stimulating microchip on the surface of the spinal cord. It's an implant, but it's a semi-invasive implant. And long and behold, this is spreading like fire because it's a 45-minute procedure, is cheap, much cheaper than deep brain stimulation. And independent laboratories around the world have shown in more than 100 patients, Parkinsonian patients, that you can get something that is very critical in Parkinson's disease, that is freezing, gait freezing, which you cannot treat with anything so far. You alleviate dramatically the gait freezing in these patients. Those are venues that I think that can be explored in the future, but they're very clear, very focused.
Yeah, definitely. There's maybe easier ways and non-invasive ways like what you were saying, but I think Neuralink did make money because a few months after they showed that monkey video, they raised over $200 million investment. So I think that's a success.
Well, no, success until they can pay off that $200 million.
Good point, yeah.
They raise that money and they don't produce the equivalent or more, a return at 8 times or 10 times. It's going to be very funny to see the face of those guys who put the $200 million there. So I think it was much more focused on that, marketing to raise money rather than actually showing long-term survival capability. And that's my problem. Look, the hype may be good at short term, but at the long term, you're going to have a lot of people knocking your door asking, where is my return?
Yeah, definitely. Definitely. So you, as we're doing the recording, you're currently in Brazil, but before that, you are in Duke University. So you're joining previous guests, Mikhail Lebedev and Warren Grill from the Duke group of people. And before we started recording, you said something interesting that you were going to choose to become an emeritus at Duke, and that you're setting up an institute in Brazil. Do you want to talk about both of these things?
No, I have set an institute in Brazil 20 years ago as a volunteer. We created in 2003 a project that later became a large collaboration with the Brazilian government, and it became the campus of the brain in the northeast of Brazil. It's a state on the coast is the capital of the state on the coast of the northeast of Brazil. And that institute has developed over these 20 years. It had education programs, it had a women's clinic, a couple to a neuroscience institute, which has matured to a very high level. And I'm very proud of that. But I was always a volunteer since the creation of the project. I'm chairman of the board of the foundation that supports the institute, but as a volunteer. And in parallel, throughout these years, I was, of course, a professor at Duke University. And what I said was that last July, I decided to become a different kind of scientist. So since I had already crossed 27 years at Duke University, which is the limit that you can opt for the future of your career is in your hands then. Duke offered me this emeritus professorship, and I decided to put in practice a long-term plan that I had since I created the institute of basically using the Institute in Brazil as the headquarters of an international effort to deploy all the therapies that I created over my career worldwide. So we are basically starting the process. Of course, the pandemic is a big impediment right now, but we are starting the process of creating a network, both a clinical and a basic science network that will be supported by sponsors and by a startup that will basically allow us to take all the brain-machine interface therapies that we created in Brazil and in the US to different parts of the planet, like Africa, Europe, South America, Latin America. And in that sense, I'm going to be basically coordinating this research and this deployment of this network and creating a new institute as part of this effort that started 20 years ago. We already have a neuroscience institute, but I decided that we need something bigger because brain-machine interfaces is more than just neuroscience now. And there are ramifications and spin-offs in many areas. So that gives me more freedom.
Yeah, definitely. And so basically it was started 20 years ago, but then now you're really going to put a lot more effort into it now that you have a little bit more flexibility. Do you want to talk about it? Like, how big is it so far? Is it like so many, I don't know, surgeons or patients, all this kind of stuff?
Yeah, we have, to give an idea, we created an integrated program when we started in Natal. It was called Education for Whole, because in addition to doing neuroscience research, we wanted to show that entities like this could be very important for the development of underdeveloped communities in Brazil. So we went to a part of Brazil that it has serious development and clinical, medical, social problems. And for instance, establish a program for pregnant women supporting the prenatal care of high-risk pregnancies in the northeast of Brazil, which was a huge problem in 2003. And today we are overseeing 50,000 women a year. So we have built from nothing, an entire program. In fact, when Brazil had, in 2016, you may have heard about this, the Zika virus, which is also another RNA virus, had a huge pandemic. And the epicenter in Latin America was Colombia and Brazil. Our clinic was one of the first ones to detect the Zika virus in children being born in the state. And because these kids had all sorts of problems like microcephaly and developmental issues. So this program has grown tremendously. And now we have a neuro rehab program. So in addition to the women and the children that we oversee, we are now taking care of spinal cord injury patients based on the experience that we acquired with the World Cup project. So that center is now being enlarged to become a regional center. So we are going to be able to oversee a large number of spinal cord injury patients, taking advantage of all the experience that we obtain with the World Cup. And our idea is basically to form partnerships with countries that want to implement the Walk Again project or the Walk Again rehab program, like we did here in Brazil, to oversee the neuro rehab of patients around the world, spinal cord injury patients, stroke patients. So it was interesting that this was all developed independently. And after the World Cup, we were able to put this together, and now we are ready to go international. And I think I almost like creating a distributed hospital or distributed medical school. And so I can be now a distributed dean without the need of following all the day-to-day operation of a typical academic setting, which after 40 years, I think I had enough.
Yeah, no, that's really cool. I think it's a great thing. And obviously you have ties to Brazil, but is there any other advantages to having it in Brazil versus Europe or US or Australia, something like this?
No, Brazil is just the first node. Yeah, we are negotiating with many people now around the world, and we are going to have hubs. Oh, yeah, exactly. That's a real global network. And that's the intention, is to have regional hubs that can collaborate, run research projects, deliver clinical care, state-of-the-art clinical care to spinal cord injury patients and other Parkinsonian patients. So we are creating a whole program and basically forming this network that also will have basic research goals at the same time in parallel.
So what's the next place? Where should we be looking forward to these hubs?
Oh, you're going to know in a few weeks, hopefully, when we make an announcement. Yeah.
Okay. Very cool. Yeah, no, that's exciting stuff. And then I don't know, I guess what's some timelines for opening each hubs and all. I don't know if you can share this, but
Oh no, I cannot share that yet, but that will come very soon.
very cool. Cool. Yeah. I guess in this way you'd be able to bring this treatment to more people. But is the market big enough? We were talking about earlier that the populations can't support necessarily maybe a Neuralink size thing, but maybe something like this it could, or with all the other treatments as well.
When you talk about non-invasive protocols we did for the Walk Again, we found out that yes, we can disseminate that very widely, and we did a study on that, and basically you don't even need the neuro rehab infrastructure that you used to see in the US or in certain countries in Europe to actually deliver this type of therapies. And since they are totally non-invasive and they combine virtual reality with non-invasive EEG that we have reduced now to wireless EEG and the new kind of exo that we have developed over the last few years at Duke that we are going to announce very soon, that has created a package that is absolutely affordable. And the demands in infrastructure, hospital infrastructure, are very minimal. So you really don't need much to become a hub that can, and we were thinking about that. We were thinking about countries in Africa, countries in Latin America that don't necessarily have gigantic tertiary hospital infrastructure to accommodate what people consider a modern neuro rehab center. But as we have done for the World Cup and now in Natal here in Brazil, we have a very large area in Natal. Of course, you don't necessarily need to reproduce that kind of infrastructure, but the protocols that we created may allow spinal cord injury patients to become enrolled in their therapies in these protocols immediately after the lesion, because you're using virtual reality as the first initial step for training them to learn how to operate whatever devices using EEG. So that creates a complete new way to deploy these technologies and therapies.
And then it's still at the price point where somebody in South America, Brazil, a poor part of Brazil or Africa could be able to afford that.
Yeah, that's the idea.
That's incredible. That's really cool. So yeah, I guess you got some interesting projects coming up these next few years. I think this is really interesting. Most people go a product that they sell or a therapy or something like this, but this is more opening the center with more expertise compared to just a product with the instruction manual. So I think that's interesting.
No, I think it's a different approach, which doesn't impede us to create the products. That's, of course, can be part of the program. But what we really want is to have partners that are willing to deploy this and oversee large numbers of patients being treated in their respective countries or regions.
Oh, very cool. This has been really exciting. I've really enjoyed this talk. I think this is really cool. And I've always wanted to go to Brazil. So maybe this is a good reason to go see one of those centers.
It's a good excuse.
Exactly. I think so. Dr. Nicolelis, this has been a pleasure. Is there anything that we didn't talk about that you wanted to mention?
No. I just want to thank you for the invitation. It's a great pleasure to talk to you. And I hope that we cover subjects that people will be interested in listening to.
Excellent. And then we'll see each other in Brazil.
Thank you. Take care of yourself over there.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.